Hola, bienvenidos a todos a otra sesión del coloquio del Instituto de Matemáticas. Hoy tenemos el placer de tener con nosotros a Robert Jajcay de la Universidad Comenius de Bratislava. Ha estado de visita aquí los últimos mes y medio. How long have you been here? About a month and a half?
6 months.
Oh, right, but you haven't been here that long yet.
2
You
months.
will be here.
I will be here
Sí.
6. I have
Está de
been.
visita aquí, va a estar varios meses más. Y nos va a hablar sobre el papel de la simetría en la teoría extremal de gráficas. La plática será en inglés. Thanks, Robert, for accepting the invitation, and go ahead.
Thank you. Thank you all for coming. Thank you very much. Thank you to the Institute that I have a chance to be here and work here. I have picked, this is for general audience, and so I have picked a topic that covers many, well, I shouldn't say cover, touches on many different areas of mathematics. Symmetry, that would be group theory, quite a bit of group theory. Extremal graph theory, so you probably have an idea what is graph theory. I'll make it clear what I mean by the extremal. And in fact, the talk is really a part of what people call algebraic graph theory, which means applications of algebra in graph theory. So hopefully, the talk will not go very deep into any of the particulars, but hopefully it will be interesting to at least parts of it to everybody, okay? Sorry. So the basics do come from graph theory. So I'll be talking about specific classes of graphs, and those are graphs where every vertex will be of degree k. So all the vertices have the same number of neighbors, and the number is k. And the g stands for the length of a shortest cycle. Again, a cycle in a graph is simply you traveling along the edges, you come back to where you started, and the shortest cycle of this kind is called the girth of the graph. And so we'll be interested in graphs of degree k, every vertex of degree k, and the given girth g. And we will be interested, now comes the extremal part, we will be interested in graphs of a smallest order for this particular requirements, yeah? And these graphs that have the smallest order, which are sort of the minimum possible with respect to the number of vertices, are called kg cages, yeah? I guess the word cage, I was told by people who still remember the beginnings, was a joke on the kg, so it's a kg cage, yeah, okay? All right. So what is a cage and what's the cage problem? Well, that's basically what I stated. Somebody gives you the pair of parameters, k, the degree of each vertex, girth, the length of a shortest cycle, and your role is to find at least one of the smallest possible graphs with these parameters, okay? And it's an extremal graph theory problem because you're looking for the smallest. And it's also a two-parameter optimization problem. You have the input of two parameters and you're optimizing with respect to the class. And I should stress that even though I said I will be looking for a smallest graph with the given parameters, the first thing that should be settled is, do there even exist such creatures for every pair of parameters? But the answer is yes. Okay. And the set of all the graphs with the given parameter is infinite. Okay. So it only makes sense to look for the smallest because you can make them arbitrarily large. And it's a two parameters infinite set, okay? And we don't know how to construct efficiently all these graphs, yeah? So it's not like I have the class of graphs sitting somewhere and I just go this guy, yeah? You have to construct them and you have to construct a smallest. And the order grows exponentially with respect to the girth. So the girth actually appears in the exponent. And so these graphs eventually become quite large, okay? And it's another thing I should maybe stress, but again, this is practical. It's very hard to take one graph with certain parameters and then alter it with some small smart moves to get another graph with slightly different parameters. Because this is a global property. Every vertex has to be of the same degree. If you change in one, you have to change all. And if you're gonna change the girth, you have to make sure that it happened everywhere. So it's very hard to go from one to another. And I basically already stated that we are looking for graphs in a family that we don't really have, and they are big. Okay? All right, so you may ask, well, if it's so hard, why are you interested? So yes, it has applications. I will mention some few of the applications. So one possible area of applications is network design, where the idea is somewhat that if all the vertices are of the same degree, then the production is cheaper because all the nodes are kind of the same kind. And the girth often represents how quick you can come back if something goes wrong or something like that. So yeah, and choosing the graph small, of course, is efficiency. Yeah, fewer parts, less money. Okay, and the other area that I like to mention, and that's in coding theory, there are the so-called low-density parity check codes that some of you may have heard of, which have lots of uses in coding theory. And again, they are based on the adjacency matrices of the graphs I'm talking about. Okay, and that's enough of a motivation for me. Okay, easy examples, just in case you were wondering whether there are easy examples. Of course, if you want every vertex to be of degree 2 and the girth is n, you take an n cycle. Yeah, every vertex degree 2, and you have a cycle of length n, and obviously you don't have a shorter one. Yeah. Another nice, easy example is if you want every vertex to be of degree n minus 1, and you want the shortest cycle to be a triangle, then take your complete graph on n vertices. Everybody will be of degree n minus 1, and the girth really will be 3. The last thing that I'm not checking here, it is the smallest graph with these properties, but it sort of feels like, yeah, it's as compact as it can get. So yes, it is the smallest. And similarly, if you want your girth to be 4, which is an even number, you take a bipartite complete graph. Yeah, all right. Now, these are the more interesting examples because they're highly symmetric. Yeah, so that's what I'm interested in. And so 3 examples. I'm not drawing any conclusions yet. At this moment, you're supposed to just realize how beautiful the examples are, yeah? Okay? So the Peterson graph, the Hewood graph, and the Todd graph, again, as a demonstration, everybody here is of degree 3 for the Peterson, and the girth is 5. And again, just to remind you, everybody can see a 5 cycle there, for instance, the outside, but you should also verify there is no shorter cycle than 5 cycle, yeah? Similarly, Hewood, every vertex of degree 3, and the girth is 6, and the Todd graph is girth is 8. And all of these are cages. We are able to argue that, okay? I will get to that. A little bit of history, just sort of, do you see that it's not brand new? Among the first people who studied this was Todd. Anything that Todd was doing is, in my eyes, good mathematics. So again, this is my motivation, more than the applications, really. Then Hoffman and Singleton seriously started and did quite a bit of nice work in the 1960s. And Hoffman and Singleton, of course, those of you who know group theory know that they worked in group theory as well. Fine and Higman, again, obviously, these are group theorists who just went into graph theory. And Erdős, if you're giving a talk on graph theory, you should have Erdős somewhere. If you don't know Erdős, Erdős is the god of discrete mathematics, so yeah, okay. So he actually, together with Sachs, they were the first who proved what I claimed to be true, and that is any pair of parameters, k and g, there exist infinitely many graphs with these parameters. So it's meaningful to look for a smallest, yeah? Just in case, here's Erdős. It's unfair, people always show his pictures when he's old. I mean, yeah, he was also young, but okay. Okay. And here, something that you probably have done in your introductory course to graph theory. We're going to together construct a 3-5 cage, yeah? So what are we constructing? A graph in which each vertex is of degree 3. There is no shorter cycle than 5, but there is a 5 cycle, and minimum number of vertices possible, okay? So everybody will agree that if every vertex, well, there will be at least one vertex, and if it's gonna be of degree 3, it looks like this, yeah? All right? Well, everybody should be of degree 3, so the 3 deficient vertices now get 2 neighbors, and the only question you have to ask, does it have to look like this, or could I get away without introducing one of those 6 new guys? But the answer is, if you wanted to not introduce any new vertices, you would have to connect something that's already there to something that's already there, and that would form a cycle. Okay, so if you, for instance, try to connect this guy to this guy, you would get a triangle, yeah, which is too short. This guy to this guy, you get a 4th cycle, too short. So sort of quickly, I'm arguing that if it's going to be of girth at least 5, I have to have these vertices. Yeah? Everybody has to be of degree 3, and nobody can be yet identified. Yeah? But now, I still have deficient vertices who don't have degree 3, so let's go quickly because you have taught that. I will add edges, yeah? Hoping to make everybody of degree 3 and not to create a short cycle. That's the game, yeah? All right, so far so good. The shortest cycles are 5 cycles. I have to add more because everybody has to be of degree 3. I add, and I'm done, okay? I finished. What is the moral of this fairy tale? Okay, the moral is everybody is now of degree 3. Sort of, you believe me, there are no shorter cycles, but you can always verify there are no shorter cycles than 5. And I kind of argued that I cannot have fewer vertices than these 10, yeah? Because I had the 10 and I said I cannot get away from any of them, and now I have 10, and I have completed the graph. So some summary of this fairy tale. So we positively know that we constructed a 3-5 cage. If you feel a little uneasy, yeah, if you think about it, you will agree with that. Yes, this is it. This is the smallest. He has to have at least 10 vertices because otherwise he has to have a shorter cycle. Okay? At each step, we carefully avoided constructing shorter cycles than 5. Yes, we did. At least I did. We never introduced vertices of bigger degree than 3, and the graph we ended up is cubic, has a cycle of length 5, and we only used the absolutely necessary number of vertices, yeah? So this is baby steps approach, yeah? I want to construct it, let's do it, okay? And what is it that I want to stress? The minimum number, okay, all right. This I also want to stress, but sort of you could go this way at any of these problems, except it gets big, and it gets complicated, and you don't know how to choose your edges because if you make a mistake and you cannot continue, you don't know whether it's a universal mistake and you have to add vertices or things get really complicated. The symmetry that I want to point out is that the point here is that I didn't stress it enough, but in some sense, I didn't have a choice when I was completing the graph, okay? Now this, of course, I did not convince you at all of this, yeah? But if you really tried, you sort of figure out that there must be a 6 cycle and the graph is unique. There is only one way to complete this up to isomorphism, yeah? And I do want to stress this, it's not immediately obvious, but you really have to try and then you realize I didn't have a choice here, didn't have a choice here, yeah? And so it's unique. The completion was unique. There is only one cubic graph of girth 5 of order 10, it's the Petersen, so we actually constructed the Petersen graph. That's another thing that usually you don't know what the name of the graph is that you end up with, okay? But the picture, and this is something that I will stress a lot, the picture would look the same from any vertex. Notice that I started with a random vertex. So if I started with another one or another one, I would always get the same graph up to isomorphism. What that means is that in the result, I have an graph isomorphism or automorphism between any 2 vertices. Yeah? So again, maybe this is not enough to convince you, but the point is, if it's unique, there must be a way to map this guy to this guy wherever I started. And it's the whole graph, so it's a bijection, And so it's a graph automorphism. And there will be a graph automorphism between any two vertices, yeah? In fact, Petersen has many more than just one automorphism between any two vertices, yeah? That's the note at the bottom for those who like Petersen. If you work in algebraic graph theory, it's a requirement. Okay, so once more, now the Petersen from the usual point of view, yeah? The picture that you saw before probably did not remind you immediately of Petersen, but this is how people usually draw it, okay? So another conclusion, and now comes the extremal conclusion. I claim that you can actually deduce from this one example, you can deduce some kind of a lower bound on the number of vertices if K and G are given, okay? It's called the Moore bound. Again, if you teach graph theory, you probably already taught this. But the idea is basically that if you want every vertex to be of degree K, then you start with a vertex, it has K neighbors. Each of them has K minus 1 extra because it has to be of degree K. And you keep going until you reach about half of the girth, at which point you can start joining things. So you get a lower bound on the number of vertices that is a function of G and K. And for G odd and G even, it's slightly different. But trust me, it's correct. Okay. I have recycled this slide for about 25 years, so I hope it's correct. Nobody ever called it wrong, so, all right? And the other thing that I want to mention is that okay, so this is a lower bound. I'm not claiming that you can always achieve this lower bound, yeah? It's a lower bound, it's as lower bounds go. Sometimes you can achieve it, sometimes you don't. But if you have a graph that has the given parameters and the order of it is equal to the lower bound, that automatically means the graph is the smallest possible because it cannot have fewer vertices than the lower bound. Those graphs have a special name. They are called after Mr. Moore, Moore graphs or Moore, okay? So those are very special. There you don't have the question, are you the smallest? No, it's equal to the lower bound. You can't be any smaller than the lower bound, yeah? Okay. That was one of the first things that people tried to do is to classify all the Moore graphs, yeah? So what are we classifying? Sort of a weird class. Graphs of degree K, girth G, where the number of vertices is exactly the Moore bound. It sort of looks like a hard task. It is a hard task, yeah? To classify things based on the number of vertices and so on. But it's possible to do, and the proof is wonderful, beautiful example of linear algebra. If you have not done it in your class, you should be doing it. And if you haven't seen it, you should be reading it. It's a very nice example of linear algebra, adjacency matrix, eigenvalues, integral number of eigenvalues, and things like that. So, but we know all the Moore graphs. And I should say, well, sort of. Because the last one of girth 6n and 12, they are the incidence graphs of what is called the generalized polygons, and we don't know all of them. Yeah? We know how they exist for when k minus 1 is a power of a prime, but we don't know for other things. All right, so yes, this is typical mathematics. I don't know how to solve it, so I put it into the other area of mathematics. Let them solve it, right? But yeah, the question of complete classification of generalized polygons is very hard, and it's been around for years and years, yeah? So just one more time, sort of to convince you that even though this is graph theory, it's really everything, yeah? Okay? So consider the three-dimensional vector space over a finite field FQ. I hope everybody likes those, since Galois, right? Okay. And I will construct two sets. I will construct the set of one-dimensional subspaces, and I claim there's q squared plus q plus one of them, and I invite everybody to enjoy calculating that, yeah? And I consider the set of two-dimensional subspaces, which happens to be of the same cardinality, of course, because these are perpendicular to the guys in the first class, yeah? And I consider a graph whose vertex set is the union of these two. Okay, so I now have 2 times q squared plus q plus 1. And the adjacency is simply if something is a subspace of something. So it's a bipartite graph. On the left side, if you wish, you have the one-dimensional spaces. On the right side, you have the two-dimensional spaces. And you have an edge if it's one-dimensional subspace. This space is a subspace of the two-dimensional. Yeah? It's very easy to see that it's a regular graph. Yeah? It's q plus 1 regular. Yeah? Every one-dimensional space is contained in q plus 1 two-dimensional spaces. Again, enjoy figuring all these numbers out. It's really just something maybe for the bathtub, you know. Okay? And, all right, so the girth is 6. Of that, I should convince you, and so I have a chance to use the nice board. So I claim the girth is 6. How can I convince you quickly? Oh, sorry. All right, so one-dimensional, two-dimensional. There will be no edges here, no edges here. It's a bipartite graph. And I claim that the girth is not 4. Because if it were 4, then I would have a 4 cycle. And a 4 cycle would mean that these two are contained in here, and these two are also contained in here, but that would be the same space. So this doesn't happen. 6 cycle happens. Odd cycles don't happen because the graph is bipartite. It's of girth 6. Okay? And it's a Moore graph. Okay? How can I convince you it's a Moore graph? Well, very easy, by counting. I count the number of vertices. It's 2 times q cubed minus 1 over q minus 1. And that's the Moore bound for q plus 1 and 6. Yes, it's a Moore graph. Very nice graph, right? No, you don't see any graph there, but it's a really nice graph. Okay? So this is an example of the things where we have the girth 6. Yeah, there is an infinite family for every prime power. I can do this, and I could do it for any projective plane. Yeah, and we don't know all the projective planes. But we do know that the graph exists if and only if a projective plane exists. Yeah? And so this is for those who like combinatorial geometry, projective plane of order 2, that was in the background. And the Heawood graph, which I had as a list on the list of the cages, it's a 3-6 cage, and it's also the incidence, the point-line incidence graph of the geometry, meaning on one side I have the lines, on the other side I have the points, and I connect if a point belongs to the line. Yeah? So this is related, even though some people may sneer at graph theory, this is the graph theory that's connected to everything. Okay? So, yeah? Right. So what next? Okay? So we know that, well, we sort of know the Moore graphs. Okay? So what do I know for the rest? Well, if there is no Moore graph, all I know at this point is that if the graph exists, and it does because Erdős proved that they do exist, it must be of order bigger than MKG, the Moore bound. By how much? Nobody has a clue. Yeah? And honestly, I'm not keeping anything from you. Nobody knows by how much. People don't even know whether you can always construct a constant multiple of the Moore bound. Yeah? So it's really a big open question how far you have to go sometimes to this. And one day I would like to give a talk where I solve this, but okay. All right. So the other thing is, so now we're truly looking for cages. There's no more graphs, so you are sort of in the open area. You don't even know how many vertices you should have. Yeah. So what people do is, well, people do many different things, but one way to approach this is you come up with a nice construction, okay, of something that you know for sure is of degree k and girth g. Yeah. What is a nice construction? For people like me, if it's some algebra in there, that's a nice construction. Yeah. And then you have to prove, if you want to prove that you found a cage, you have to prove that there is no smaller graph. And that's a pain. That's the typical thing in mathematics. There is no smaller graph with these parameters. How do I convince you? Do I go through all the smaller graphs and check each and every one? Well, that's usually too much work. And we don't have any good tools for this, yeah? So at this point, in this area, most people are simply happy if they find a nice construction that's smaller than anybody else's, okay? Which is, people say you shouldn't do mathematics as a competition, yeah? Well, sorry. That's how I do it. I want to have a smallest graph for given parameters, okay? All right, So proofs are hard to get. Good constructions lead to world records, okay? So what is a world record? Well, you have a construction where nobody else has a better construction for that pair of parameters, meaning smaller graph, yeah? Smallest known. This is not mathematics. It's just, what is it, smallest known? We want absolute answers in mathematics. Here you have to understand, and it happened to me. Okay, let's use somebody else. There was a graduate student in Britain who was about to defend and was very happy because he found lots of nice small graphs, yeah? And so, a foolish graph, he put it on the web. Well, my colleague, who really lost the topic, within a week, tweaked his graphs and got smaller graphs. And suddenly, the guy was a holder for 2 weeks. And then he had to defend. Well, they gave it to him, but still, okay? So this is where you very clearly feel that everybody is famous for 15 minutes, yeah? Okay. World records. Okay. I had to use the Mexican wave, so I'm sorry. All right, so how does this work? Well, people keep track of the record graphs, yeah? So this is from a survey paper. So for instance, this is a typical table. Girth this is for cubic. So all these graphs are degree 3. And for instance, the best known graph of order 13 goes to Mecke, Meerwald, and Hoare. And the lower bound is 202, and the graph has 272 vertices, yeah? And this is known for like 40 years. And notice the big difference. I mean, this is, in some sense, this is really fun because this shows how clueless we are. We cannot prove that there is no smaller graph than 272. The lower bound we have is 202. It's 70 vertices away from it. And we still can't prove that there is no smaller graph or that this guy is the smallest, or we can't find a smaller. Again, this is in 1990s. Norman Biggs already wrote that this is an embarrassment, and it's still an embarrassment. And I would like one day again, but you know, okay. All right, but this is what it looks like. So Jeff Exo, who's a good colleague of mine, has, look at the gap. The lower bound is 2048, and his smallest graph is 5376, and nobody can do better. And look here, 12,000 versus 108,000. Yeah? And by the way, these are relatively big graphs, right? Yeah? And nobody can do any better than this. And it keeps going. Of course, why do I show you more of the table? Because there's my name. Not anymore. Sorry. This was true in 2008. There are 2 guys from Britain who erased me from the table, so sorry. Okay. All right. So this is how people keep track of these things, yeah? If you get something new, well, the authors of the survey kind of watch what is being published, and if they see that something seems like a candidate for improvement, of course, we try to include it. This is a dynamic survey, but it hasn't been updated in a while because both authors are busy, yeah? Right, but yeah. Okay. But this is how people keep track. There is also a web page that is more up to date. Yeah. All right. Okay. All right. So imagine that you're one of those people who are competitive in this area and you want a world record. Yeah. So often it feels this way. Yeah. You work and work and work, and what you get is okay. Right. But what can you do? Well, you try to learn from the known examples, yeah? So, what is it? The beautiful examples, the 3 that I had there, and the 3-5 case, the one that I actually solved on the slides, suggest that maybe the extremal graphs are highly symmetric. Okay? This is heuristics, nothing but heuristics. Yeah, it looks like the examples we have are highly symmetric, so maybe there is a good reason to look among highly symmetric. Yeah? And my reason is I deal with highly symmetric, so that's my area. Please bring it on. Yeah? But it's not necessary, and in fact, not all the known cases are that highly symmetric as I want them to be. So, but there are more reasons why it's not a stupid idea. It's not just because I like vertex transitive, but highly symmetric graphs look the same at each vertex. So you sort of just solve the problem once, yeah? And then you just kind of carry it around with automorphisms, yeah? They usually have a compact description. We're talking graphs with thousands of vertices. So it's nice if you can describe the graph with a group with just 200 or 400 elements or something like that. Yeah, you have more compact description. And, okay, sorry. And sort of just from now on, we will be looking among vertex transitive graphs, okay? And that, why? Because it looks like a good idea, okay? All right, that's all. Looks. It's not mathematics when you say this looks like a good idea. Oh, what is that? There have been PhD students who couldn't finish with something that looked like a good idea. Yeah? But that's how I want to do it. Okay? So just for the record, what is a graph automorphism? I assume everybody knows. It's a bijection of the vertices that maps adjacent vertices to adjacent vertices. So that preserves the structure. The more automorphisms does a graph have, the more symmetric it appears. Again, now I'm appealing to the sense of beauty. If it's very symmetric, it's beautiful because somehow we are genetically programmed to like highly symmetric graphs. Yeah? We are born with the likeness for highly symmetric graphs. All right? And specifically, what do I mean by highly symmetric? I mean vertex transitive, which means that between any two vertices look alike. Yeah? I have an automorphism from any vertex u to any vertex v. So that means the neighborhood of u is the same as the neighborhood and all the way through the whole graph. So they all look alike. Yeah? Okay, if you thought I was done with arguing that this is a good idea, for example, all the Moore graphs are vertex transitive. So those are the ultimate solutions. They are vertex transitive. There must be something to look in vertex transitive. Another argument, these are the settled cases. These are the cases cubic up to girth 12, which is really, again, only up to 12 we can solve the problems. Yeah? At 13, you saw the big gap of about 70 vertices that we don't know what happens in there. But for the known cases, the bold-faced guys are vertex transitive, and even the non-bold case guys have large orbits of vertices. So even though they don't have a single orbit of vertices, but maybe 2 or things like that. And lots of automorphisms. Yeah? Okay? And so just to continue my argument that vertex transitive is good. So there are some infinite families of graphs of large girth. For instance, all of them based on algebra, so that's why I'm mentioning that. The so-called sextet graphs, which are sort of, yeah, now you have sextuples of things over a finite field. Or you have the Lubotsky-Phillips-Sarnak construction, which is based on Cayley graphs of linear groups. So I'm not going to go into this, but these are really some of the best constructions, and they are all algebra-based and highly symmetric. Okay? So at this point, when you look at the tables, the majority of the best constructions take advantage of symmetry. Okay? That's, again, just a statement based on visiting situation. Vertex transitive graphs are the same locally around each vertex. Here is yet another important thing. And if the graph is vertex transitive, to check the girth, is not all that hard. In general, to check the girth, you have to visit every part of the graph. But if the graph is vertex transitive, you check locally whether there are any small cycles. And if there are no small cycles here, there will be nowhere because it looks the same at every point. Yeah? So you save considerably on verifying the girth of the graph. Okay? So each vertex lies on the same system of cycles, which means that if there are no short cycles in the neighborhood of one of the vertices, there are no short cycles at all. And now this is extremely useful because we're now talking maybe about cycles of length 14 in a graph of size 20,000. So you save a lot if you just have to look around within like distance 7 from your vertex. You're visiting a fraction of the graph, and if there is no short cycle there, you know there's no short cycle in the whole graph. Yeah? So this is extremely useful. Okay? And I already stated that in my previous lectures that I almost never give a talk which doesn't have Cayley graphs. So here's another justification why I want to use Cayley graphs. In some sense, they are the simplest examples of vertex transitive graphs constructed from scratch. Okay? What do I mean by constructed from scratch? Because there are many known families of graphs that are vertex transitive, but they sort of happen to be vertex transitive. This is constructed with the goal of being vertex transitive. Okay? So this is what I said, like Johnson graphs, which are based on subsets, or generalized Peterson, which are based on arithmetic and so on. Some of them just happen to be highly symmetric. But Cayley graphs, from the very beginning, you know that your graph will be highly symmetric. I'll give you a definition, don't worry. So here it is. How do you get a Cayley graph? You start with a group, and you take a generating set. All that you require of the generating set that is closed under inverses. So if an element has an inverse different from it, so it's not an evolution, put it in there, and don't put 1 there. Yeah, that's usually people don't put 1 among generators anyway. Okay? And what's the graph? The graph has for its vertex set the group elements. So the elements of the group are the vertices. And each vertex G is connected to everything you get from G by multiplying by the element in the generating set. Okay? So a vertex is connected, you multiply G times x1, you get a new element, gx1. x1 is not the identity, connected. gx2, gx3, and so on, connected. Okay? So here's a quick example. People have already seen this who were attending my previous talk. So here's an example, Zm cross Zn. Yeah? It's very simple. Group, generating set 1, 0, 0, 1, n minus 1, 0, n minus 1. Clearly it's a generating set. I get both coordinates. Is it closed on? Clearly it's closed under inverses. And what does the graph look like? Well, locally, when you start from the vertex 0, 0, it's connected to everybody you get by adding one of the 4 to 0, 0. Well, here they are. Yeah. All right, so 0, 0 will be of degree 4 and connected to this guy. If you do the whole thing for every vertex, you get this grid with the, I need to stress that this actually goes there, yeah? So it's kind of closed on the torus, if you wish, but I'm not talking topological graph theory, yeah? But this is what the graph looks like. If you're trying to be quick, the degree of the graph is the size of the generating set, yeah? And so this is, okay. Once again, you can do this with any group, any generating set closed under inverses. By the way, closed under inverses, you're just making sure that you don't have direction, yeah? If you go one way with one of the generated, the opposite brings you back, so you don't have to worry about direction of in the graph, okay? Why is it interesting? Okay, sorry, I didn't say that, I should have. So why do I said these are vertex transitive. Left multiplication or addition by the elements of group, all of those permutations are actually graph automorphisms. Okay, I apologize. I should have prepared a slide with stating that. I just live with the fact forever, so I forgot that people need to be reminded. But Cayley graphs really, the left multiplication in the group for every element gives you a bijection on the vertices that preserves adjacency. And so Cayley graphs always have a vertex-transitive automorphism group isomorphic to the group you started with. So all the Cayley graphs are vertex-transitive. That's why I like them. And then I forget to argue that. But it's true. Cayley graphs always are vertex-transitive thanks to that group you started with. Okay? Well, all right. So I say, or other people say that too, consider Cayley graphs and look for KGs there. Okay? Well, the first question, again, that should come to your mind is, okay, Erdős proved that for every K and G, there exists a graph. But now we're restricting ourselves. We want to look among Cayley graphs, which is definitely a tiny fraction. Almost all graphs are asymmetric, so Cayley graphs are just an exception in some sense in the world of graphs. So does there exist for every K and every G a Cayley graph with this degree and this girth? Okay? That's the first question you ask, because if it doesn't, then it's not worth much looking for the smallest guy among Cayley graphs. Okay? Well, Bix again proved, I don't have the exact year, but it's 1980s, that for any K and G, there is a K regular graph whose girth is at least G. Yeah? I should say vertex transitive, but that's what I mean. Yeah? So in fact, he proved that there exists one that's Cayley. Yeah? Beautiful construction, really, really nice construction. Highly recommended for the bathtub again or something. It's actually easy to understand, but such a nice idea. Not doing it. All right, but the point is, at least, he doesn't have complete control of the girth of his graphs. He just knows that they have a large girth, okay? But doesn't have control. And in fact, we still don't know what the girth of those graphs is. All we can show that it's large, yeah? And whatever you say you want it to be, you can make it bigger, okay? All right? Then for vertex transitive in general, not Cayley, two colleagues of mine, Roman Nedela and Martin Škoviera, proved as a byproduct in 2001. This is a paper about topological graph theory, but they happen to prove that for every pair Kg, there exists a vertex transitive graph of degree K and girth G. Yeah? So precisely now, yeah? Not anymore, just, okay, precisely. So this is nice. So what that says is, for every vertex, for every problem, I can look for vertex transitive graphs. I cannot guarantee that the vertex transitive graphs I will find will be the smallest among all graphs. Okay? I just argued that they stand a good chance. Yeah? That's not the same as saying that they have to be. But if I just in the game of beating everybody else, if I find a vertex transitive graph that beats everybody else, I'm happy for a while. Yeah, but okay. All right? So, but this was proven that for every K and G, there exists a vertex transitive, so it makes sense to look for a smallest vertex transitive. And for many years, I was giving talks, this is 2001, and trying to convince people that we need a construction of Cayley with exactly the parameters. Yeah? And I was telling people, nobody was doing it, so what the heck. We proved it with Josef Širáň, that for every K and G, there exists a Cayley graph of degree K and exactly girth G. First proof based on maps and finite residual groups of automorphisms. Next proof based on Bix by playing with his construction. And one more proof that I have. So since then, we have 3 proofs, but okay. But now we know that looking among Cayley graphs, at the very least, will produce something. Yeah? But it's going to be the smallest, we don't know. Okay? All right? So, okay. Now I'm talking about Cayley graphs, so some questions about Cayley graphs. The first thing, if somebody gives you a Cayley graph, what is its girth? Well, one thing is you put it in a computer and you just calculate. But let's use group theory, okay? So here's a Cayley graph. Its elements are and edges are always labeled by an element from the generating set. Yeah? So what is going to be a closed walk? From here to here, you get by multiplying by x. Then you get multiplying by x2, x3, and so on. And once you come back, what is going to be the total product? Well, you started here and you came back here, so you multiplied by 1. So the total product of the labels of the edges you visited is going to be 1. And that's exactly what I'm saying. That each closed walk in a Cayley graph, so it doesn't even have to be a cycle, closed walk, is associated with a reduced word in the generators equal to 1. Okay? Reduced mean we don't use the hair, what people call hair, that you go somewhere and you immediately come back through the same edge. Yeah? So, how do you determine the girth of a Cayley graph? It's the length of a shortest reduced word in the generators equal to 1. Okay? So this is completely now a group theoretic question. Somebody gives you a group, set of generators, what's the shortest word? Yeah? Of course, it's still hard, but okay. Also goes the other way. If somebody gives me a reduced word, which is equal to 1, that gives rise to a closed walk in the group. Okay? So, the graph theoretical question, you may feel that I often avoid graph theory and try to use groups. Yeah. Okay. Right? So the girth of a Cayley graph, given group and generating set, is equal to the length of a shortest non-trivial reduced word equal to 1 in the generators. Okay? Okay, that's nice because it's a group, now it's a group theory thing. Yeah? So, quick revisit. Remember the Zn cross Zn with the generating set of 4 elements that we had there? In fact, it doesn't matter what you pick for your generating set. Whatever you pick for your generating set, xi, xj, if you have at least 2 guys in there, xi, xj, xi inverse, xj inverse is 1. Why? Because the group is abelian. Yeah? So if you pick an abelian group, I just proved that if you pick an abelian group, your Cayley graph will be of girth at most 4. Yeah? Why? Because no matter what you choose for your generating set, there will be a closed thing of length 4. So it could be of 3 if one of the generators is a product of the others. Okay? All right, so yeah, if G is an abelian group, so this is true for all the abelian groups. Okay? So if you want to construct graphs with large girth, what's the moral again? Stay away from abelian groups. Yeah, all right. So it has girth at most 4. Okay? So how far should you stay away from abelian groups? That's another nice question. Yeah? So abelian bad. So what's good? Yeah? Well, then the first thing to look at is the nilpotent groups, because most people believe that they are the closest class to the abelian groups. And okay, so what are the nilpotent groups? If you take a group, you construct the lower central series where you recursively calculate those commutator things. And if it terminates in finitely many steps, then it's a nilpotent group. And the length doesn't depend on how you do it. It's always there, the same number. And so that's called the nilpotency class. Okay? And the bigger the nilpotency class number, the further the group from being abelian for most people in group theory. Okay? So it's the class that's close to abelian, but the bigger the number, the further you are away. Okay? And so you look at that, and together with Marston Konder and Jeff Exo, we were able to show that, sort of like the abelian case, if you know the nilpotency, you have an upper bound on the girth of a Cayley graph. Okay? And I should maybe stress that I don't claim to be this to be really, really deep. It simply means understanding what it means the nilpotency is new, and then sort of coming up with a short word. Well, short with respect to that. Yeah? All right? So what is, again, the moral? That if you want to use nilpotent groups for your constructions, you need to use nilpotent groups with increasing nilpotency, because otherwise you stay within a range for your girth. Okay? All right, so if you don't like nilpotent, well, let's generalize. Solvable. I'll go quickly. So for solvable groups, you have the derived series, And let's just do it. For solvable groups, again, there is a number associated with each solvable group. It's the length of the derived series. And it's solvable if it's finite, so each solvable group is associated with a specific number. And the point is, again, there is a bound. Okay? So if you take a solvable group with derived series of length n, then the bound on the girth is at most 4 to the n. Okay? Notice the huge improvement. Before that, the nilpotency class was nu plus 1 squared. Now we have the derived length in the exponent. But still, what it means, stay away from solvable groups with short derived series. So what's the best? Stay away from solvable groups. Yeah? All right. Okay. The proof, I have the proof on the slides. But here, basically, the proof just tells you how to find the word of length 4 to the n if the derived length is n. Yeah? Commutator of commutators, it works. Yeah? It's not really a proof, it's a hint how to do it on your own. Okay? So this is the game we're playing at this point. That is, we're gonna use Cayley graphs and use groups that are more promising than others. Which are more promising? Non-solvable. What's the problem? Well, slightly harder groups, but okay, yeah, right? So I just have maybe not even 5 minutes, but let me just say, yeah, for a while we played this game, worked with Cayley graphs, and then it transpired that no, that's not the best. All right? So what did we do? Again, I have to go quickly through this. I had lots of examples where the Cayley groups do play a nice role. The Lubotsky-Phillips-Sarnak, they construct so-called Ramanujan graphs, which are asymptotically some of the best constructions for the cages that are known. They use projective special linear groups. We just taught that yesterday that they are not solvable, right? So I've taken advantage, yeah? No. So in the remaining time, absolutely irresponsibly, too quickly, what's the new construction that we use now? It's called the voltage graph construction. And again, just take my word for it. Voltage graph constructions have recently replaced many of the record holders on Cayley graphs. So yeah, so you switch, okay? If other people are gonna beat you with this construction, you use it too. Okay. So very quickly, what is it? You start with the graph. Now make the edges actually into opposing arcs and assign to each arc an element of a group. Yeah? So graph, each element, if dart gets an element of the group, the only requirement is that opposing darts get inverses. And then you can construct what is called the derived regular cover, or most people will say lift of gamma. And the lift of gamma is a new graph constructed with respect to gamma and with respect to the group that you assigned. The vertices are the original vertices where each vertex is multiplied by all the elements in the second coordinate, all the elements of the group. So the new graph has order, previous graph times the size of the group. Yeah. So all the elements, this is the vertex and this is the group element assigned. And where is the adjacency? Over there. Picture will help. This is the bottom graph, and these two guys are joined. They become associated with the group elements. And who do you join this guy with? You join it by multiplication again, like in Cayley graphs. This was assigned the element G, so you take the guy assigned this H, and here this will be GH. Yeah? So it tells you who's connected to who. Okay? You say this is too quick. I have to agree. I disapprove, but I don't have more time. So 2 examples. Petersen is not Cayley, and it's constructed this way from a 2-vertex graph. Hewood, another cage, constructed from a 2-vertex graph. So then we just decided that that's what we're going to study. Okay? And I have to, I can't do this. I'm sorry, but this is the graph that we determined, again, by sort of practical trying things. This is the graph that's the best base graph. And we learned that eventually, okay, let's just go to the result, okay? Maybe I should say that. Why do voltage graphs outperform Cayley graphs? Here's the answer. The answer is, in Cayley graph, if you have a short cycle, it does show up in the Cayley graph, and it does create a short cycle. But even in this voltage graphs, some short words cannot be read and cannot create a short cycle. So this has a better potential simply for the reason that not everything bad that happens in the group has to happen in the graph as well. Okay? Very quick explanation. So now you can see the comparison. If you use voltage assignment from a solvable group, instead of 4 to the n, the largest possible girth, it's 6 to the n. That's why the voltage graph guys beat the Cayley graph guys, yeah? Because you can simply go further with the same thing. And I think I should now finish. Final comments, okay? You should. Sorry? Sorry? Solvable. Yeah, this is for solvable. We don't have any bounds for non-solvable of this type. They probably are, there are some, but it must be some different idea. I can't choose commutator, nothing like that. Okay? Right. You should have asked whether lifts are vertex transitive. No, they're not. That's embarrassing. I keep saying that's the best possible thing to do is vertex transitive, and now I'm advertising for graphs which are not. But they are still highly symmetric in the sense that the group that you're using, I guess it says there, acts regularly on the fibers. Fibers being these things that you get from vertex by doing all the elements. So they act regularly on those, and so transitively for sure. And the entire thing that it comes from the voltage group acts semi-regularly on these of the same size. So it's still very symmetric, okay? Most current holders have been constructed using solvable voltages, okay? And one could resort to using non-solvable, but non-solvable tend to be big. And maybe there are other bounds. That the fact that we don't have them doesn't mean there are no bounds for non-solvable. But I should say that the records that we had with JFXO that were eventually erased were based on PSLs with this construction from the base graph, what we call the theta graph. Yeah, so it worked for us. Okay, that's it. Thank you very much.
¿Hay preguntas para Robert?
Thank you, Robert, for your talk. It was very nice. I'm very sorry I was a bit late, and maybe you mentioned with the Moore graphs that there's still, the smallest undecided, I think, is degree 57. I'm not an expert on Moore graphs or anything. And you were saying just when I arrived that you would expect them to be vertex transitive, so you would look for vertex transitive, and now you just said that they might not be. I read somewhere that if there was this undecided Moore graph, that it would not be vertex transitive. Is that true?
Okay, thank you for asking. I did not stress the fact that when I said that we know almost everything about Moore, I stressed the fact that there's an infinite family where we don't know all that much. But there's also this one open case, and it's a fun case because when you do the linear algebra, it excludes everything but the degree 57 and girth 5. It doesn't exclude that. A Moore graph with these parameters, 57 and 5, might exist. Linear algebra doesn't kill it. It kills everything else, but doesn't kill this one. And and that's a big, people call it the monster or whatever you want to. Nobody knows whether this creature exists or not, yeah? Because it's a specific graph. Degree 57, girth 5, and we know the order. It's the Moore bound for 57, 5. We just don't know whether the graph exists or not. It's too big. It's about 5,000 vertices. So it's too big to do any exhaustive search or anything, so nobody knows whether the graph exists, and nobody has a nice proof to kill it. Okay? I've seen 2 proofs where they killed it. Both were wrong. The community was excited. Everybody was reading, and then there was a disappointment because there was always a hole. Nobody has killed it. But what Eugenia said, and it's correct, we can prove that if the graph exists, it's not vertex transitive. Okay? Which for most people like me means the graph doesn't exist, because if it's not beautiful, it cannot exist, right? But that's not really a mathematical, even I admit that's not a mathematical proof. All right? So yes, it's actually known that the maximum size of the automorphism group is something like 325 versus 5,000 vertices. So it's not only not vertex transitive, if it has automorphisms, it has very few. And this was proven by Shiran and Jajcay, 2 of my colleagues from Bratislava. Originally, the non-vertex transitivity was, I think, by Aschbacher or somebody, and yeah, but yeah, the 325, I think, goes to Jajcay and Shiran. So that's a beautiful mystery. Most people believe the creature doesn't exist. Some people even prove it. Yeah, and I would like to see the solution to that, but I firmly believe the creature doesn't exist, because if it does, it's really weird.
¿Alguna otra pregunta?
A very basic question. Are cages unique in the sense that
No.
there can be 2 different
There
cage
could be
cages?
several different.
I see.
For girth 9, I believe there is like 12 of them or something. Okay, the number is sort of right, but yeah, you can have there is no proof that it has to be unique.
Pair of parameters.
And especially after you get really far from the Moore bound, there is a potential for many graphs of the same order with the same parameters. With my students, what we have been doing is sort of investigating this question for orders, even once you know the cage, for bigger orders, how many graphs and things like that. So it's a very meaningful question, and it's also related, okay, in some sense you didn't have to ask me, because you have many projective planes, non-isomorphic projective planes for the same parameters. They give different graphs. And all of them are cages. So in that sense, I'm fully answering your question. You can have lots and lots of even non-Desarguesian cages.
Sorry, another question. When you mentioned the paper by Martin Scovira and Roman Neděla, and then your paper about the existence of the vertex transitive graphs, and then the existence of the Cayley graphs, are the Cayley graphs always smaller?
No.
Oh, no, there's no
Actually,
relationship
if you
there.
think of it, Cayley graphs form a subclass of vertex transitive. So if you restrict yourself to a smaller class, you're going to end up occasionally with, the extreme example is Petersen. Petersen is vertex transitive, non-Cayley of degree 3, girth 5, and order 10. The smallest Cayley graph, degree 3, girth 5, has 50 vertices.
Okay.
So it's 5 times, the smallest Cayley is 5 times bigger than the smallest vertex transitive for this specific example.
Okay, thank you.
¿Alguna otra pregunta? I wanted to ask something. These graphs that you mentioned by Lubotsky, Phillips, and Sarnak, those are like an analytic number theorist, functional analyst, and a group theorist. What were they doing?
What they were doing?
Yeah.
They like my problems. No, they really were after Ramanujan graphs. Which is, so these are characterized by the second largest eigenvalue.
These expander graphs.
But it turns out that being a cage and being a Ramanujan graph is, the second largest eigenvalue does sort of have information about the girth and things like that. So they were after Ramanujan graphs, where the second largest eigenvalue is greater than or equal to some bound. However, what they constructed turned out to be also the best thing in cages. Okay, so in some sense now I agree with you. They were not after cages originally,
Yeah.
but they ended up having constructing cages, and in some sense they are still the best, like as asymptotically for infinite family, they are among the best constructions.
¿Alguna otra pregunta? Si no hay más preguntas, démosle las gracias a Robert.
Thank you.